In the last lecture, what we were looking at this complete linkage algorithm implementation for a data set which a distance matrix given by the following. So, previous to this complete linkage clustering algorithm, we had looked at the single linkage clustering algorithm, and we had starting from a distance matrix, we had constructed this single using the single linkage clustering algorithm, the dendrogram clustering tree and its interpretations were discussed. And we had started this complete linkage algorithm implementation with a distance matrix which was the same distance matrix as what we had used for the simple single linkage algorithm. We had come up to this step number 2, wherein at the first step we had seen that the cases 3 and 5 were merged at a fusion level of 2, and then we were required to do the updation of the distance matrix, which we had done in the last lecture and had come up with this modified, or rather the updated distance matrix. Now, we start from this particular point. Now, if we look at this distance matrix now, we will have to look at which two clusters can now be merged. In order to do that, we will be looking at which of these mutual distances that is given in the updated distance matrix is the minimum possible. So, as we see here that this 5 is the minimum among all these off diagonal entries, and hence we will be merging case number 2 with case number 4 and form a new cluster with these two cases. So, we move on to that particular step here. Step 3 is to merge 2 and 4 at this fusion level 5. If I remember correctly, that is at a distance level of 5. So, we will be keeping this particular information similar to the previous information that we had kept, that we are forming this new cluster. Previously it was 3 5, now it is 2 4. So, this 2 4 forms a new cluster at a fusion level of 5. So, that is an information that we need to retain and carry forward, because we will be using this information. This is that second bit of information which we will be requiring in order to form the dendrogram tree. Now, once we look at this particular distance matrix, now neither 2 is a separate identity nor is 4 a separate identity, and hence the rows and the columns corresponding to this would vanish. So, we will not be having any entry corresponding to this 2, this 4, and similarly corresponding to this 2 row here, and the column 4 here will not be present there. What will be present there is the number of clusters now are 3 in numbers. What are the clusters? The clusters now are 3 5, 2 4 and 1. So, we will require distance matrix updation. So, that is the next step of this implementation of the complete linkage algorithm. So, this is the distance matrix updation. Now, the new distance matrix is going to be 3 by 3 as we have discussed. So, that will be having these now as the clusters. Now, 3 5 was an existing cluster in the previous step. Now, we have formed a new cluster which is having cases 2 and 4, and there is one more case which is 1, which is already in the existing list of clusters. So, we will have this 3 by 3 matrix filled up. Now, this is corresponding to that 3 5 cluster. This column is representing from this cluster here. The second column is from 2 4 cluster, and the third column is from this 1 cluster. Now, note that there are some entries from the previous distance matrix here, because the distance between 1 and 3 5, which is 11, will be an entry here which will be carried forward from the previous table, previous distance matrix itself. However, when we are trying to now look at the distance between 1 and 2 4, or 2 4 and 3, which would come out here, needs to be calculated. So, for the distance matrix updation, the distance between the cluster 3 5 and the cluster 2 4 needs to be computed. Remember, we are looking at a complete linkage distance, and hence the distance between cluster 3 5 and cluster 2 4 would be given through that maximum of the mutual distances. That is what would lead us to a complete linkage among these. So, the distance between 2 and cluster 3 5 and the distance between 4 and 3 5 would now be computed. What are these two distances? From the previous table we will be getting this D235. D235 is 10. So, this is going to be maximum of that 10 entry, and distance between 4 and 35, similarly distance between 4 and 35 is 9. So, what we will be having is maximum of these two, that is 10, to represent now the distance between these two clusters, which is 35 and 24. Now, similarly one have to obtain actually the distance between 1 and cluster 24, 1 and 24. So, for that we will be requiring the maximum, because we are on a complete linkage platform. So, we will be requiring the distance between 1 and 2 and the distance between 1 and 4, which can be looked at from the previous table itself, and which is equal to 9. One can verify that that is equal to 9 actually. So, we come up with this as the modified or the updated distance matrix at step 4, when we now have 3 clusters in place. Now, the next step, once we have an updated distance matrix, that is step number 5, is to now look at this updated distance matrix and then find the minimum distance in updated matrix, updated distance matrix, updated distance matrix is what we have, as we can see, is 9. So, this is 9. This would imply that we will merge the cases accordingly. So, now this 9 is the distance between a singleton cluster 1 and a cluster which is having 2 cases 2 and 4, and hence we will be merging 1 and 2 4 at a fusion level of 9, 1 and 2 4 at fusion level 9, and we would require actually this information to be preserved, because we 1 with 2 4 is now merged, 1 and 2 4 are merged, 1 and 2 4 are merged at a fusion level of 9, and that is the information which we need to keep track of. This is the third information when we are adding the information one after the other. After those two, we will be having this third information, which would be an information which would be required actually to form the dendrogram tree, right. Now, we come to the next step, that is step number 6. So, at step 6, we will look at updating this distance matrix. Previous distance matrix was 3 by 3 because we had 3 clusters. Now, we have got 2 clusters now. One cluster is an existing cluster 3 5, and the other cluster is the cluster which is now formed, which is having 3 cases 1, 2 and 4, and hence we will be having the distance matrix which is just a 2 by 2 matrix. 3 5 is an existing cluster, and 1 2 4 is a cluster that is newly formed. So, this 2 by 2 matrix will have zeros in the diagonal, and this is the distance between this cluster and this cluster. Using a complete linkage distance philosophy, one can similarly find out what is the distance between these 2 clusters. It turns out that this particular distance is equal to 11. So, this would imply that the last fusion is merging the cluster 3 5 and the cluster 1 2 4 at fusion level 11, right. So, the last information, that is what we will be having, is the following, that this 3 5 cluster merges with the cluster 1 2 4 to form a single 5 unit cluster at a fusion level of or merger level of 11. So, this is the fourth information that we will be keeping. So, we have all the 4 information. This is the first fusion level, this is the second fusion level, this is the third fusion level, and this is the fourth fusion level. Then the last step of this algorithm is to draw the dendrogram diagram. Step 7 is the dendrogram diagram or the dendrogram tree formation. to give the hierarchical clusters. To give these hierarchical clusters. Let us do that on the next slide here. So, what we will be having, similar to the single linkage distance, here the maximum merger level is 11. So, this is the merger distance or the threshold distance that is on the y axis, and we will have these 1, 2, 3, 4, 5, say this is fusion level 5, 6, 7, 8, 9, 10, 11. So, this is the 10 level here. Now, what are the information that we will be putting here? First, we will put in the information that 3 and 5 have fused at level 2. 3 and 5. So, there are cases which is 3 here, this is 5 here, they have merged at a fusion level of just equal to 2. So, they are the nearest among all the pairs of objects. So, that is the first information. So, this we have taken care of this one. We will next look at the second information, then 2 and 4 have merged at a level 5. Let us see. So, it is 2 and 4 have been merged at a level 5. So, this is that level 2 merger, this is that level 5 merger, case number 2 and case number 4 are merged to form a new cluster, right. So, we have taken care of this one. Now, what we are next going to have is input number 3, 1, 2 and 4 merged at level number 9. So, the case 1 comes in here. So, there is single stick here which is coming up to this level of 9, that is the merger level 9, and then this 2 cases 2 and 4 and 1 now come together to form a new cluster. That is what this input had given us. So, we have taken care of this too. So, the last thing that we need to do is that all the cases now merge at level number 4. So, we have this one cluster which is having these 3 cases 1, 2 and 4. We have another cluster 3 and 5, and then they come together, these 2 clusters come together at a fusion level distance of 11, and that is the dendrogram tree. So, we will have this as the dendrogram tree, wherein the clusters are in a hierarchical form, and with this we have formed from that distance matrix D by implementation of a complete linkage algorithm. Now, an important point to be noted in these type of hierarchical cluster analysis is that how to decide on the viewpoint of looking at the clusters being formed. So, when we are looking at deciding the viewpoint in a dendrogram tree, now if we look at this particular point, that deciding the viewpoint actually, let me correct it, viewpoint or the reference point actually from which we are looking at, whether to look at the dendrogram, because if we look at this level 11, we have all the 5 cases in one cluster. If we look at this 9 level here, we will have then 2 clusters, one having 3, 5 and the other having 1, 2, 4. So, which distance is desirable? There are various ways actually of looking at this deciding upon the viewpoint. A simple approach is to look at the following diagram, which looks at the following. On x axis we have the number of clusters. So, this basically is to decide the number of clusters, and on y axis here we will have this as the fusion levels or the merger levels. Now, for this particular dendrogram, if we look at, suppose this is say I divide it here at 5 here, this is 10, this is say 11, right. So, there say number of clusters is 1, 2, 3, 4, 5. So, there are 5 cases. So, at the most we will have 5 clusters. Now, if we look at fusion level number 11, fusion level of 11 out here, then we will have one cluster here. Now, if we look at a fusion level of 9, so this is say fusion level 9, if we look at fusion level 9, we will have two clusters. So, we have the second point here 9. If we look at a fusion level of 5, which is this one, we will have 3 clusters in the data. If we look at a fusion level which is 2 here, so if this is 5, then let us say this is 4, 3, 2, 1 say. So, the fusion level of 2, we will have this as 4 clusters, and then this graph is up to this particular point, because number of clusters 5, that would be at the 0 level of fusion. So, we have a graph like this, and it is basically from such a graph look for the flattening actually of the graph. The point at which the graph flattens, the point at which the graph flattens is the desired viewpoint. So, we will say that from this point onwards, well, this is a very small data set, and hence the flattening of this particular graph is not observed here. If we have huge number of cases, then what it will turn out is that we will have such a graph with many number of clusters, and we will find that if we have, for example, a graph of this following nature, that it is of this nature, then this is the point which we associate with the flattening point. So, this is what we associate as the flattening point, and there will be a number of clusters, say G, for this particular point here, and this G is usually taken as the viewpoint for looking at the number of hierarchical clusters that are formed from this particular data set. Now, we move on to the other type of clustering algorithm, which is non-hierarchical clustering. Non-hierarchical clustering. We will discuss one important non-hierarchical clustering method, which is called the k-means clustering, or the method of iterative relocation method. So, what are the features of such a non-hierarchical clustering method? So, the features, the salient features would be that the clusters are not clusters formed, do not have any hierarchy, do not have any clusters, correct this one, clusters formed do not have any hierarchy. Number 2, there is no distance matrix calculations, as contrast to the previous hierarchical clustering method. No distance matrix calculation, we start with the raw data and end up with the raw data only. No distance matrix calculations. Now, it is said that it is better suited for a higher or a large data set, better suited for large data sets. Why is that so? Because if we look at the output of an hierarchical clustering, if we have a huge data set actually, then the number of cases may run into hundreds and thousands, and in such a situation we will have all such mergers, the cases, this x axis will be so crowded with all those cases for a high dimension, for a large data set, then it would be very difficult actually to make out which clusters are formed at which particular level, and hence the output will be so cumbersome for a hierarchical cluster analysis output. It is better suited if we have a non-hierarchical clustering, and we do not talk about any hierarchy in the formation of the clusters. Now, how what is the type of algorithm, or what is the type of behavior of such non-hierarchical clustering method? Non-hierarchical clustering method starts either clustering methods starts from either number 1 an initial partition, initial random partition actually, initial partition of items or objects into groups, or it starts with an initial set of, starts either with an initial partition of items into groups or with an initial set of seed points, initial set of seed points. I will talk what I will explain what I mean by seed points. Now, these seed points will actually act as, will form the nuclei of initial clusters. So, what are we trying to do here? We are trying to do in the non-hierarchical clustering is the following, that if we have n cases with us, we are basically trying to put these n cases into k number of beans, k number of beans in the sense that k number of clusters. So, each of these k beans are identification levels for each of these clusters, and then naturally there is not going to be any hierarchy between these bins, all of these bins are different. So, we will have such k clusters in the data as the final output of this particular system. So, they do not have any hierarchical structure in the formation of the clusters, there will be no distance matrix calculation as we will see, and this is better suited, we have already discussed. And this non-hierarchical clustering method, how do they start? Well, when we have a hierarchical clustering method, we start with what? We start with a distance matrix. When we have a non-hierarchical clustering method, it starts basically with either an initial partition of items into groups. So, if we say that there are k clusters in the data, we will start with an initial randomly chosen k clusters, which are basically the partition of the data set, either with that, or we start with k seed points, k multidimensional points randomly chosen. It may be chosen from among the existing data, or maybe just p dimensional k such seed points, which now act as the centroid or the nuclei of the initial clusters. So, these are the two ways in which a non-hierarchical clustering method actually starts. I will just put it as a note that when I have said that we start either with this or with this second initial set of seed points, how one can actually do that. One way to start is to randomly select seed points from among the data itself, from among the items, because each of these items are the p dimensional in nature, and when we talk about seed points which are going to form as the nuclei of the initial clusters, which are going to change iteratively, those points also needs to be of the same dimension as that of the data, and thus choosing initial set of seed points, say k in number, would be to look at randomly choosing k points from among the n possible items. Now, this is one way which would take care of this particular approach, or what we can do is to randomly partition the data, to randomly partition the data. So, it is random partition of the data, that is items or objects, into initial groups. Right. So, that is how one usually implements this two different type of approaches. We will look at one example. In the example, what we will do is we will approach the first, we will adopt the first approach, that we will have initial partition of items into groups, and then we will see how this method of k-means clustering is going to evolve. Now, as I said that the k-means clustering, k-means method, or the method of iterative relocation or the method of iterative relocation is an important clustering approach which actually leads us to non-hierarchical clusters that can be formed from the data. Now, a k-means method, I will just explain how this particular method actually goes about. K-means method is an algorithm. K-means method is an algorithm that assigns each object to the cluster having the nearest nuclei or centroid So, we will be having all such possible clusters, and then this k-means method actually will assign a particular object to a cluster if that cluster's centroid is nearest to that particular object when that object is being compared with the centroids of all the possible clusters into which the object can actually go to, right. Now, what is the algorithm for this k-means method? The algorithm goes in the following steps. So, the first step is to partition the data, partition the items into k initial clusters. This is one approach. We could have also put k centroids into that particular initial data and then make the assignment accordingly. Now, first we partition all the possible n items into k initial groups, and once that is being done, then we reassign, we look at possible reassignment, reassign items to the cluster whose centroid is nearest in Euclidean sense. Then once we have done that, we would recalculate the centroid for the cluster receiving the new item, and for the cluster which is losing that item, receiving the new item, and for the cluster losing the item or the case, right. So, what we are doing, we are looking at k initial clusters, and then we are looking at whether a particular object is closest to its own cluster, that is in the initial cluster, whether it is nearest to that or which to which centroid of the initial clusters, k initial clusters, that item is closest to. And if we find that a particular item is closer to another cluster than to the initial assigned cluster, we will make a reassignment, and once a reassignment is made, we will have to recalculate the centroids, the k centroids, for two specific clusters, one cluster which is receiving the new item and the cluster which is losing that particular item. And then we will continue this particular method of assignment reassignments until we find that no reassignment is possible. So, we will look at repeat step 2 until no more reassignment is possible. Right. So, it is basically in this 3 simple steps, we will look at a simple data and then try to see how this k-means algorithm method actually goes about. Now, I just put it as a note what I said, that rather than starting the process of this k-means algorithm with a partition, a random partition of the data, random partition of all items into k initial groups. That is what we have written in the algorithm as in step 1 of the algorithm. We can also assign seed points. We can specify k initial centroids straight away, which are going to act as the seed points, and then proceed to step 2 of the previous algorithm. Step 2, after a walk through the data, right. Why do we do that? Because once we have specified k such initial seed points, these may be k randomly chosen multidimensional items only, then we need to actually look at we have to look at all the data, and then we will have to look at these initial centroids. How do these centroids behave as far as the data is concerned, because if a particular case is nearest to a particular chosen or rather randomly initialized seed point, we will have that point to be associated with that centroid, and we will have a cluster around that particular seed point, wherein the case which is closest to that particular centroid or the randomly chosen seed point is belonging to. And then we walk through the data, go to step 2, and then look at possible reassignments in the data that can be possible, and then the algorithm goes through. Now, let us look at a numerical example to illustrate how this k-means clustering algorithm actually behaves. So, this is an example. We have the following, that we have items. To make life simple, we just take 4 cases A, B, C, D. So, these are 4 items or 4 cases in the data, and let us assume that these are, each of these cases are having 2 dimensions. So, these are all 2 dimensional data. So, that the first case is characterized by this vector 5 3, the second is characterized by this vector -1 +1, and then the third case is characterized by 1 -2, the third case, fourth case or case D is characterized by -3 -2. So, this is the data what we have to start with, and we will look at, starting with this data, how to get to a k-means cluster. Now, let that k be equal to 2 for this given illustration. So, we are trying to divide these 4 cases into 2 clusters using a k-means clustering approach, which is going to lead us to clusters which are non-hierarchical in nature. So, since we have this k equal to 2 at the first step of implementation of this k-means clustering algorithm, let us look at an arbitrary partition of the data. So, we need to have 2 elements in the partition, arbitrary partition. Say we take one partition to be A B and the other partition to be C D. So, we randomly put A and B in one cluster, C and D in the second cluster. So, this corresponds to the first cluster, this corresponds to the second cluster. Now, we will have to first look at, if these are 2 randomly formed clusters, then what are the centroids of these, and then look at possible reassignment to some other cluster different from the initial random cluster. So, we will have to look at this cluster centroids in this particular data. So, we will have these as the 2 possible clusters, and these are cluster centroids. This is the cluster AB, this is the cluster CD. Now, if you look at the cluster centroid, it is nothing but x1 bar, actually you can say, and this is x2 bar. So, where x1 bar is the mean of the first component of the two elements which are belonging to the first cluster, that is case A and B. So, this cluster centroid, which is the cluster AB, would be having the coordinates as the mean of these two as the first coordinate and the mean of these two as the second coordinate, and hence both of them are 2 in this particular case. Similarly, for the cluster which is having elements CD, we look at what are these quantities. It turns out that this is -1 and this is -2, right. So, these are the centroids. Now, we have these two clusters. This is the centroid. Suppose I say that this is centroid number 1 and this is centroid number 2. So, this is centroid number 1 and this is another random cluster which is having this centroid number 2 as that. Now, there are two cases A and B here and C and D here. So, we will look at whether A case is closer to this centroid center or the other centroid center. These two clusters may not be so different. So, we might be having the clusters C and 2 as this point. So, there are cases C and D sitting here. So, we will find out the distance between A and this cluster center, A and this cluster center, and try to see whether A is closer to this cluster center than to the other cluster center, and then look at possible reassignment. So, that goes into the second step of this algorithm. So, in the step 2, we will look at that assignment. So, in the second step, we compute the distances, as I said, that compute distances from cluster centers, from cluster centroids, and reassign items if possible or if required to the nearest group. Now, that is possibly going to happen because we had just the initial set of clusters to the nearest group. Now, for the given data here, we are looking at this to be one centroid and this to be the other centroid. So, what we are going to do is to look at the distance of A from its cluster center and distance of A from the other cluster center. Now, if we find that the distance of A from its own cluster center, initial randomly chosen cluster center, is higher than the distance of A from the other cluster center, we will reassign A to this cluster. And once we do that, we will stop at that particular point and then recalculate the centroids of the clusters, because this cluster is now losing A and the other cluster is going to gain A, if that is possible. If that is not the case, if we find that A is closer to its own cluster, own initial cluster, than to the other cluster which is containing the points C and D, then we will not disturb A, keep it in the same cluster as what it was present in the initial randomly allocated clustering. Then we will look at the second case and look at whether any reassignment is required for that point or not, and then we will continue. At any point, if we find that a reassignment is done, we will stop at that particular point, and then what we are going to do is to recalculate the centroids of the clusters, right. So, let us look at what we are going to get here. Now, if we are looking at the distance square of A from the cluster center, now by saying this, I am saying that this is a centroid of AB. We will have to look at this, we will have to, this is for case number A, right. So, we will look at the distance of A from its own cluster, distance of A from the cluster center or the centroid of the cluster which is CD cluster, right. Now, it is easy to see what these quantities are. It turns out that this is equal to 10, this is the Euclidean distance square, and this distance is 61. So, A is closer to its own initial cluster than to the other cluster. So, this would imply no reassignment of A is required, right. Now, once that is done, we move on to case number B, and we will calculate the similar thing. We will have to look at the distance square of B from its own centroid, and we will also have to look at this distance square of B from the other cluster centroid C and D, as it turns out that this is equal to 10 and this is equal to 9. So, B is the distance of B from its own cluster center is higher than the distance of B from the other cluster, which is C and D. So, this would imply that B, the point which was initially sitting in the cluster AB, is closer to the other cluster than to its own cluster, and hence reassignment of B is required. So, we will need to do this because we see that B is closer to the cluster CD than to the cluster AB. This would further imply that reassign B to CD. Now, the setup gets changed as B is reassigned to CD. So, the new clusters are, there is one cluster with singleton case A, and there is another cluster with these three cases B, C and D, right. So, since we have this as the two new clusters, we will require updation of what? Centroids, updation of cluster centroids, because the previous centroids were that for the randomly allocated terms there. So, this is basically going to be the step 3, because we had at step 2 that reassign, I am sorry, this is going to be step 3, this is going to be step 3 of this implementation, updation of the cluster centroids. Now, what are the clusters now in the data? As we had said that these are the clusters. This is cluster number A, and the second cluster is having these three cases, and these are centroids. It is similarly that x1 bar corresponding to the cases under this, x1 bar corresponding to the cases under the second cluster, and this is going to be that point itself because it is a singleton cluster. So, this point is the cluster centroid, which is the ordinates of A, and for this BCD cluster one can calculate that this is now the new cluster mean centroid point of this cluster. Now, once we have that, we will have to look at possible reassignments. Possible reassignments meaning thereby we will have to see whether A, the distance of A from itself is always 0. So, A cannot be reassigned here. We will look at what is the distance of B from this center, and what is the distance of B from this center. We will look at the distance of C from this point here and this point here, and look at possible reassignment. Now, we will have this particular table, the squared distance to group clusters. We can have the following table, that we are looking at items which are A, B, C and D. We will have to look at the distance of each of these items from the two cluster centers, one this and one this. So, we have got a cluster as A and another cluster as B, C, D, right. And we look at what is the distance of A from A, that would be 0. The distance of A from this particular point here can be obtained, which is 52, and similarly this table can be completed 40, 41, 89 and this is a 4, a 5 and a 5. So, this for example denotes the distance of the item C from A cluster's centroid, and this denotes the distance of C from this BCD cluster centroid. Now, we see that A anyway cannot be reassigned. We first look at B, the distance of B and the cluster center A is 40, this is 4, and hence B is correctly put into this set. So, no reassignment for B is required, neither for A. Then we look at the item number C. C is closer to the cluster centroid which is having the points B, C, D than what it is to A, because this is smaller than this, and hence no reassignment is required for the item C. And also for D, we find that it is closer to this cluster centroid than to this cluster centroid, and hence no reassignment also for D is required. So, this step is going to tell us that no reassignment further is required. And if that is the case, then we terminate this particular procedure and finally say that these two are the two clusters in the data which are thrown up by the k-means clustering. So, this would imply that this 1 and it is, oh I am sorry, it is not 1, it is A and BCD, A and this BCD are the desired clusters. Right. So, we have just two clusters in this particular data. Now, the next thing that is what we are going to look at is some sort of optimality criterion in deciding, or some sort of approach of comparing different partitions or different clusters in the data. So, that is the last thing which we are going to see. After that, we will look at some real life data and look at how the clustering for such real life data actually behaves. We will be actually looking at many such criterion. So, we look at clustering criterion, that is basically for comparing different partitions or different clustering levels, comparing different partitions of the data. Now, what is the basic objective of looking at this type of criterion? The objective is to have a criterion for optimum partition of the data, for an optimum partition of the data such that given a set of cases which are going to be clustered, the problem reduces to partition the data into G clusters. Now, G is a number which has to be derived, clusters, so that the clustering criterion is optimized, so that the clustering criterion is optimized. Because as we have seen say in the hierarchical clustering approach or in the non-hierarchical clustering approach, we can have different clusters, different partitions of the data. Say if we are looking at a hierarchical clustering algorithm, if we look at two different fusion levels or the threshold distances, then we have completely different clusters in that particular level, and hence there has to be some way of comparing such clusters, whether we should look at a particular say 2 clusters in the data or whether to look at 3 clusters in the data, what is going to give us some sort of optimality with respect to some criterion that we are going to propose shortly. Right. So, that is what is the basic objective of this particular analysis. Now, let there be n data points, let the n data points. Now, these are cases be given by say x 1, x 2 and x n. Right. Now, given this particular data, the sample variance covariance matrix, is given by this, we have seen time and again, say sigma hat, which is say with a divisor n, so that it is corresponding to the maximum likelihood estimator. So, that is I equal to 1 to up to n x I minus say m, where m is the sample mean, x I minus m transpose, where this m vector is 1 upon n summation I equal to 1 to n x I. So, this basically is the sample mean. Right. Now, let us define the number of clusters. Let there be G clusters. We are trying to compare, or rather have a platform for comparing such possible clusters. Let there be G clusters and define this following indicator function z j I to be equal to 1 and 0, 1 if the case x I belongs to cluster J and is equal to 0 if it is otherwise. So, if z j I is given by this, we can write the following quantities. We can write that our m vector as following. So, this m vector, say I have that, say m j vector, this is going to be the cluster mean for that jth cluster, which is going to be 1 upon n j. n j is the number of points in that particular cluster, and this is summation I equal to 1 to up to n, the entire data, z j I, that into x I, wherein we have n j to be equal to summation z j I, these indicator variables, for I equal to 1 to up to n. Right. So, this is the mean of cluster J, and what is this? This is the number of items in cluster J. This is simple to see that, because if you look at z j I is equal to 1 if x I belongs to the jth cluster, and if we have n j items among this small n to belong to cluster number J, exactly n j of them among these z j i's for a particular j would be equal to 1, and hence the sum would be equal to n j only, cluster or not. So, these two are the two simple quantities. Then we can define the two following quantities: the within cluster sum of squares and cross product matrix, sum of squares and cross product matrix is going to be given by say S w, which is equal to 1 upon n. We will still use that indicator function. This j is equal to 1 to up to g. So, these are the number of clusters, and I is equal to 1 to up to n. Then we have this as z j I, the indicator. This is x I minus m j. This is the cluster center for the jth cluster, x I minus m j transpose. Right. So, this is also called the pooled within cluster, scatter matrix, over the G clusters. Now, if this is the within cluster sum of squares, one can define also the between cluster. So, the between cluster sum of squares and cross product matrix, sum of squares and the cross product matrix is say S B, which is equal to sigma hat minus this S W, which is going to be given by simple subtraction. This is going to be given by this n j divided by n, and then we will have this as m j minus m into m j minus this m, where m is the grand mean. So, what is this going to indicate? This is going to indicate the scatter of the cluster means about the grand mean, right. This is of the cluster means, because we are looking at the deviation of this m j from m, the grand mean corresponding to all the clusters, and we are looking at how that is being deviated, right. So, this is what is termed as the between cluster sum of squares and cross product term, and the previous is what is called the within cluster sum of squares and cross product matrix. Now, the optimality criterions for clustering are basically based on these two measures, SW, SB and sigma hat, which we will see in the next lecture. Thank you.